You've probably heard the phrase big data, but what does it actually mean? Data science involves making sense of data, taking insights from it, and perhaps linking it in with algorithmic systems which can do further work on it. Generally speaking, having more data to work with is better, all things being equal. That is, assuming the same level of quality, integrity, etc. As well as this, some machine learning methods, such as deep learning techniques, gain a disproportional benefit from very large amounts of data. Big data involves collecting a mass of data together, even if it might be from different locations or time periods, in order to discern if the aggregated data can tell us something more than just the sum of its parts. DIKW pyramid. First, let's take a look at the word data. Most people think that data and information are synonymous, but there is a difference. The DIKW pyramid helps us visually see the relationships between those terms. Data is the raw form of input. It's unfiltered numbers, words, patches of colour, or audio phonemes. Data isn't really useful on its own, especially once the databases become so large that you can't see it all at a glance. For example, let's say that you have a database full of keywords extracted from articles. In itself, that doesn't really tell you anything. Information is data that is useful to businesses to help make decisions. It has been organized and interpreted, sufficient to place it into categories. Keywords can be organized by cluster to show frequency of use, or by dates to show historical trends. Now they start being useful. Knowledge is information set into context. It leads to action. With some further context, our word cloud can be linked into associated groups of similar articles, illustrating the semantic trends even without needing to be explicitly structured. Wisdom is knowledge built up over time so that prior experience informs new decisions. By placing knowledge within a historical pattern of prior outcomes, one can infer or predict that readers who enjoyed one article will be likely to enjoy similar kinds, even if not using the same types of keywords per se. Big data involves collections of data that are massive in scale and require advanced tools to process and analyze. It is often described in terms of the V's of big data. There are perhaps as many as 10 of them. The first 4 describe the nature of big data: volume, variety, velocity, and variability. Volume is the magnitude of the data. Some databases can be enormous, social media content, for example. Variety. There are many sources and types of data, such as audio, image, video file, text data, log files, user activity data, machine and sensor data, etc. Additionally, data may be a mix of public, confidential, or restricted forms. There may be a variety of different rights, obligations, or jurisdictions attached to different data points or sets. Velocity. Data from multiple sources may be collected at different frequencies. Business information systems, for example, may integrate different data on a per second, per day, and per month or even quarter basis. Variability. Even similar data can still have some sudden spikes or odd outliers. Does the data adhere to a general mean or to a curve? Or does it contain some wild differences based upon, for example, seasonal cycles? The final 6 V's describe the usefulness of data. Veracity. Is the data truthful? Does it have bias, noise, or other abnormalities that are not representative of the entire population? Is the source of the information trustworthy, and can events be corroborated in some manner? Did the data come from a faulty sensor or other questionable input source? Does the data include biases that may create a skew during processing? For example, a sensor which is better at hearing higher pitches may record more female participation in conversation compared to male, even if that may not be the case. Validity. Is the use of this data correct and accurate for an intended use? Is the data sufficient enough to draw meaningful conclusions from? Was it collected in a manner that can be directly compared to a new situation? For example, if a weight is consistently heavier than it should be, then that can be compensated for because it's consistent. However, if it were variable, then any data from that would be automatically invalid. Vulnerability. Is the data at risk of being intercepted, stolen, or altered? Sensitive data is, of course, particularly worthy of protection. Volatility. How long can the data be considered valid? After a period of time, would the data be no longer accurate? For example, data on how occupied a public square is will have a half-life of usefulness as people enter or exit over time. Data on the occupancy of a roller coaster is likely to be very involatile, but only for as long as the ride is scheduled to run for. Visualizability. How challenging is this data to visualize? For example, we might be able to put in some time series data into a graph or an audio signal into a waveform. But disparate points of data might be quite a challenge to create a dashboard from. More exotic means of displaying information might be required. This makes deriving meaning from data more difficult, as well as debugging potential issues. Value. What value can be derived from the data? Does it easily translate into tangible benefits or actionable insights? How difficult or expensive was it to obtain or process? Can bringing it together with other data increase its value? Does it constitute valuable intellectual property?